So the Taylor series is when we represent any function using the power series. So basically our ultimate goal is, if we're given some continuous function, we would like to write this as the summation of some infinite polynomial or infinite power series. For example, previously we've considered an example 1 over 1 minus x can be written as 1 plus x squared plus x cubed and so on, x in the power of 4 and so on, where x is between -1 and 1, right? So this is coming from the geometric series. So now what we want is we would like to find out the power series form of any function. So in this form, the only unknowns here are the coefficients c0, c1, c2, c3 and so on. So we need to find the general formula for finding them. So let us set x to be equal to the a. So for x is equal to the a, if I set up the x is equal to the a, the power series becomes f of a, right, is equal to the c0. If I substitute x to be equal to the a for all the terms, it simply is going to be equal to the c0. So now, in order to find the c1, I need to get rid of this term, right? So in order to do this, I need to take its derivative. So let's find the derivative of the fx. It's going to be c1 multiplied to the 1, right, plus c2 multiplied to the 2, x minus a in the power of 1, plus 3 multiplied to the c3, x minus a in the power of 2, plus, you may guess that the next term is 4 multiplied to the c4, x minus a in the cube, plus and so on. So when x is equal to the a, the f prime of the a is simply equal to the c1 because all the other terms are going to vanish, right? So now we know the general formula of finding the c0 and c1. So we can continue taking the derivatives in order to find the formula for the c2, c3, and so on. So let's take the second derivative. If I take the second derivative here of this function with respect to the x, it's going to be 2c2 plus 6 c3 multiplied as x minus a plus 12 c4 x minus a in the square plus and so on. So in order to find the c2, we need to set x is equal to the a and find the value of the second derivative of the function at the point a. So this is going to be equal to the 2c2. From here we can find that the c2 is equal to the ft prime of the a divided to the 2. So let's find the c3 in the same form. So for x is equal, so first of all we need to take the derivative of the f, the third derivative of the f with respect to the x. So the first term is going to vanish, the second term is 6c3 plus 24c4 multiplied as x minus a, right, plus and so on. So in order to find the c3, we need to set x is equal to the a and find the value of the third derivative of the function at this point a. It's going to be 6c3. So from here we can find that the c3 is equal to the third derivative of the function at the point a divided to the 6. Right? So let us write down all the coefficients which are found in a sequence. Right? So c0 is going to be f of a. c1 is the first derivative of the function at the point a. c2 is equal to the second derivative of the function at the point a divided to the 2. The c3 is equal to the third derivative of the function at the point a divided to the 6, right? Which can be written as a 3 factorials. And so on, right? So can you guess the general form of the coefficient cn? So probably it's going to be c n's derivative of the function at the point a, at the central point of the power series, divided to the n factorials, right? Indeed, this is true. For example, if I substitute n to be equal to the 1, it's going to be f prime divided to the 1 factorials. If I substitute n to be equal to the 0, f of 0 means that it doesn't mean the power of the f, right? It means the 0's derivative, which is the same as the function itself, right? Divided to the 0 factorial, which is 1. When n is equal to the 2, it's going to be f second derivative of the a divided to the 2 factorials, and so on. So please note that this notation means n's derivative of the function. So in this case, we can write down the any function f of x, any continuous function f of x, in the form of the power series. N goes from 0 to infinity. So Cn is going to be written as the n's derivative of the function at the point a divided to the n factorials multiplied to the x in the power of n. So this series is called the Taylor series. So the special case of the Taylor series, when we're going to center the power series at around 0, so when a is equal to the 0, we can write down the function in the form of the infinite sum from 0 to the infinity, f n of 0 divided to the n factorials x in the power of n, and this series is called the Maclaurin series. So let us expand a couple of functions in the Taylor series or Maclaurin series in order to illustrate how it works. Example. So let's say we're given a function f of x is equal to e in the power of x, right? So in this case, we would like to write this using this formula, right? Using this formula. So f of x is going to be written. So f of 0 plus f prime of 0 multiplied to the x plus f 2 primes at the point 0 multiplied to the x squared plus f3 prime divided to the t, f3 primes at the point 0 divided to the 6 multiplied to the x cubed, and so on, right? So we know that any derivative of this function, the first derivative, the second derivative, and so on, all of the derivatives are going to be equal to the e in the power of x simply, right? And so that is why all of the values of the derivatives, basically f prime at the 0, f2 prime at the point 0, or f3 prime at the point 0, and so on, for all the values of the n's derivative of the function, it's going to be e in the power of 0, which is equal to the 1, right? So that is why we can write down e in the power of x is equal to 1 plus x squared over t plus x cubed over 6 plus x4 divided to the 4 factorials, 24, plus and so on, right? So we can write this down in a form as the summation n goes from 0 to infinity, x in the power of n divided to the n factorials, right? So it appears e in the power of x can be written as the sum of or as the infinite polynomial, right? So actually, we can get a value of the e using the polynomials. For example, if I would like to evaluate the value of the e, I need to set x to be equal to the 1, right? And I need to set all the values of the x in the right-hand side part with 1. So it's going to be 1 plus 1 plus 1 over t plus 1 over 6 plus 1 over 24, and so on, right? So when you take some fixed amount of the terms here, it's going to be a really close value to the t.71, right? It's already t and half, and you add some values, and if you take, for example, 10 values, it's going to be really close to the t.71. If you would like to get more precise value of the e, then you need to take more terms on the infinite series. So now let us expand the sign effects in the power series and the Taylor series. So let's consider another example. So our function is going to be sine of x. So again, we would like to write this down, this function, in the form f of 0 around a is equal to the 0 plus f prime of 0 multiplied as x plus f2 prime of 0 divided to the t multiplied as x squared plus f3 prime of 0 x cubed divided to the 3 factorials, and so on, right? So let us find the first term. So sine of 0 is equal to the 0. So the first term is equal to the 0. When n is equal to the 0. When n is equal to the 1, the second term, it's a derivative of the sine, which is cosine of x, right? And the cosine of 0 is equal to the 1, right? So the second term is going to be simply x. So the third term, when n is equal to the 2, it's going to be derivative of the cosine, which is minus sine, right? At the point 0, it's going to be 0. So the third term, when n is equal to the 2, also doesn't exist. When n is equal to the 3, it's going to be derivative of the minus sign. It's going to be minus cosine. The 0 is going to be minus 1. So that is why when n is equal to the 3, it's going to be minus x cubed over 3 factorials, right? So you might guess that n is equal to the 4, it doesn't exist. And when n is equal to the 5, we need to take the derivative from the sine, right? Because when n is equal to the 4, it's going to be derivative of the minus cosine, which is sine of 0, which is 0. And when n is equal to the 5, it's going to be derivative of the sine, which is plus cosine of 0, which is 1. The term here is going to be x5 divided to the 5 factorials. So you might guess that sine of x can be written in the form x minus x cubed divided to the 3 factorials plus x5 divided to the 5 factorials. So the next term is, again, the odd power of the x, but it comes with the minus. It's going to be x7 divided to the 7 factorials, then plus x9 divided to the 9 factorials, and so on. So in a sigma notation, we can write this down as the summation of minus 1 in the power of n goes from 0 to the infinity, right? So if I substitute n to be equal to the 0, the first term is plus, the second term is minus, the third term is plus, and so on, right? Multiply to the x in the power of tn plus 1 divided to the tn plus 1 factorials. So indeed, if I substitute n to be equal to the 0 here, it's going to be x in the power of 1 divided to the 1 factorials. When n is equal to the 1, it's going to be x in the power of 3 divided to the 3 factorials. When n is equal to the 2, it's going to be x in the power of 5 divided to the 5 factorials, and so on. So in general, the sine of x can be written in this form using the Taylor series.